Okay, so we're answering a few questions from chapter 3. So this one is from lesson 3.5, number 28. Is that correct, on 28?
Yeah.
So 28, they're asking us to find the complex conjugate of each number. So what we were given is this, and a conjugate, if we just think about, if we forget that for a minute, a conjugate, when we learned about conjugates, and some people may have never learned about conjugates when you factored, it depends on your teacher. They should have taught you about conjugates. But when we have binomials such as this, x minus 3, x plus 3, they're conjugates of each other, meaning the first terms are identical and the second terms are just opposite sign. And so when they multiply together, they make the perfect difference of squares. And so we want the complex. So this is going to be 9. And then the square root of a -3 is really, oh wait, is that a square root? Oh, 9 minus the square root of 3. Oh, so I see what these are all, that's all the real portion. So there's an imaginary portion that you're not seeing, which is silly. So this is really just 9 minus the square root of 3. There's no, because this is like an invisible plus 0i. So the conjugate would be a minus 0i, but there's no imaginary piece there anyway. The ones that they had here in the book were not great to choose from. So for instance, 26, let's do that because that one is actually a valuable one. So on 26, I always write my real piece first. So it's really 4 minus 2i. And then the conjugate of this would be 4 plus 2i. And the benefit of the conjugates is when we are working with the rational in the rational functions in 3.7. Have we gotten to that piece yet? Because this might be.
No.
Okay, so I'm going to give you a heads up for 3.7. So when you multiply these together, just like up here, these conjugates don't have a middle term when they multiply. We're going to use these because when we rationalize our denominator, kind of like if you've ever rationalized a denominator where you've got an irrational like square root of 3 there, you have to multiply by the square root of 3 over the square root of 3, right? So that this becomes the square root of 3 over the square root of 9, which is the square root of 3 over 3. So you have to multiply. So this no longer becomes an irrational number. So you're going to do this in 3.7. You're going to actually create a conjugate. You're going to multiply by the conjugate so that when you multiply, you get 4 times 4 is 16. And then you get a minus 8i in the middle plus 8i in the middle. So those middle terms go away. And then you end up with a negative 2i plus 2i. So this is a minus 4i squared. I squared is always equal to a -1. So this becomes 16 minus 4 times a -1. And that simplifies to 16 plus 4, which is just 20. And so you're going to use this thinking of the conjugates to multiply by the conjugate on the top and the bottom, like we multiplied by the square root of 3 over square root of 3, so that your denominator now becomes 20 instead of having this complex imaginary number in the denominator.
Okay.
So it's down the road a couple of sections, but
yeah. Is 28 already solved then?
So this number 20?
No, 28.
So 28. So 28, yeah, it's just 9 minus square root of 3 because that is a real number, even though, well, find so the complex conjugate would just be in 9 minus 3 square root of 3 because that's all a real number. Even though square root of 3 is an irrational number, that's all real. So I don't know why they did that. Because if
Okay.
you look at 27, that should still be 3 plus square root of 2 in the back, no? Let's go check it out. And that's from 3.5. 3.5, 27.
Mm-hmm.
Yeah.
Hmm.
All the examples that they put in here, I'm going with the flow with this book because I just showed up on the scene on January and I'm like, I got to teach out of the book they're using, which is fine.
Yeah.
But they don't, to me, they don't give a lot of great examples for you to play around with this conjugate thing.
Okay.
Just my example, does 26 give you enough support there?
Yeah.
Because you're
Yeah.
going to need this for later on.
Yeah. And then I also have a question on 54. I solved it all and then I went to go check my answer in the back of the book. And it's, I think they like simplified it or something.
54 probably isn't in the back, right? The evens aren't there.
Oh, maybe it wasn't 54.
Let's see.
I don't know, but I don't think it's right. I don't think I simplified it enough.
On 3.5, on 54, and 3. 54 says compute the zeros of each quadratic function. Oh, so 54, because it is only 2 terms, you can just set it equal to 0 and solve for the 0. So by adding 10, oh no. I just realized I did it in my head and I just realized it is a complex number, but it's fine, it'll work out. So negative 3x squared equals 10. And then when we divide by the negative 3, we get x squared equals a negative 10 thirds, right? And then when we take the square root of that, we get x equals plus or minus the square root of 10 thirds. And then an I out front, because taking the square root of a negative makes you have the imaginary number. And you could take it a step further so that you don't have a rational number in the denominator. So actually with the example that I did up here with the square root of 3, we could take this plus or minus I, the square root of 10 over the square root of 3, and multiply to get the square root of 3 out of the denominator. So if we multiply by a square root of 3 over square root of 3, we'll have plus or minus I. The plus or minus I takes care of there being a negative in this when you take the square root here, right? We can't take the square root of a negative number, so the I takes care of that. Then we have the square root of 30 over the square root of 9, and that's a perfect square root. So this is plus or minus I, the square root of 30 over 3. That works for me. I would have accepted this to the square root of 10 over 3, but you really should rationalize the denominator.
Okay.
If just a heads up for everybody on the recording, if you're going on to calculus, you should be rationalizing the denominator. If you're done with after this class with math, then don't stress about it. Just between you and me.
Yeah.
I mean, there are things you need, are you going on to calculus, hon?
I don't think so.
Well, then you should be. Any other ones so far that you wanted to go over?
I think that was I think 63 was the one I was actually talking about. Now that I get to looking at it. I don't know. Maybe I did it right.
Well, let's check it. What did you?
There was one that I looked in the back of the book and I just didn't have the right answer. But I don't remember if it was this one.
63 isn't.
Yeah, it is 63.
Okay, and they're asking us to find the 0, right? find the solutions of the quadratic equation, relate the solutions of the equation to the zeros of an appropriate quadratic function. Okay, so we have a negative 3x squared plus 2x minus 4 equals 0, because that's what it means to find the zeros. And so if we use the quadratic equation, we've got a is a negative 3, b is 2, and c is a negative 4. And that means we're going to take our zeros would be the opposite of b, so a negative 2 over, I'm sorry, a negative 2 plus or minus. The square root of b squared is 4 minus 4 times a times c, all over 2a. A negative 2 plus or minus the square root. So we have 4 subtracting positive 12 times 4 is 48. So a minus 48 over a negative 6. With me so far?
Yep.
So a negative 2 plus or minus the square root of 4 minus 48 is a negative 44 all over a negative 6. And then the negative 2 over the negative, well, we better wait on that because let's simplify what we can out of the square root. So the square root can be the square root of 4 times the square root of a negative 11. Really, we'll call it a positive 11 times the square root of a negative 1. So the square root of 4 is 2. The square root of a negative 1 is the I, and then we have to leave that square root of 11 as the irrational piece. And then we have a negative 2 over, so 2 and 2 are both factors of 6. So the only way you can cancel anything out of the 6 is if you either completely split this into 2 fractions, which we could because it would be a complex number and they want us to look at this as zeros of the appropriate quadratic. So we have, this is going to be a negative 2 over 6 is going to be a positive 1/3 plus or minus. Then this 2 over 6 is going to be plus or minus I over the square root of 11. Let's see here. So these are the zeros. Now you can see from Desmos, did you put this one in Desmos? When you put this one in, this is not, my Zoom is hesitating here. Okay, there we go. So let's turn that one off. So when we put this one in Desmos, we have y equals negative 2x minus 4 plus 2x minus 4. Yep. So because of the negative 3, it's face down, and because its highest degree is a 2, they're both face down. And so we can see we don't have any real zeros. So when we go to look at this, as far as the zeros, if we were to write it in the polynomial function, we have to use, I want to see how they worded that again. Relate the solutions of the equation to the zeros of an appropriate quadratic function. Oh, so this is just going to be, these would be set equal to 0, what we have there. They wrote theirs in the back of the book a little bit different than I would write them. So I always put my I out in front of my radical so that it doesn't get mistakenly inside. But this is basically how you're going to write the zeros.
Okay. Yeah, I didn't take the square root of 4 and the square root of 11. I just
Um,
left it 44.
Yeah, if you can simplify it more, try to do that.
Okay.
Yep.
Alrighty.
Yeah, you're getting there. Any other questions? So that gets you through 3-5. So you've just got 3-6 and 3-7. Oh,
Yep.
you answer. Was your other question part of 3-6?
No, I haven't even started 36 yet.
Oh, question number 25 was from 3-4.
Yeah.
Okay, I'll go back and look at that one. Okay, there was another question then on 25 from 3.4. And so the first thing you're going to do is pull out the x from this polynomial. And then you're going to look at all the factors of all of your possible rational factors, which it would be your constant divided by your coefficient on your highest term. And so it would just be all these possible factors are +1 or -2, +or -3, +or -4, 6, or 12. So you can use Desmos to find one. So I'm going to show you how. So I would just type in your original equation, which is this one right here in red. And you can see, if you click on the graph, you can see them all here. So I mean, it would validate what your end answer should be. And I've been trying to encourage everybody to do that. So the 0 that I'm pointing to right here is the x that we already pulled out. So that's done. Now we're looking at, you can pick either of these. You could pick a -3, you could pick a -1, or you could pick 4. So I chose to use a -1. So I'm going to go back to my paper, and we know that x gets pulled out, and I'm going to use a -1, which means that x is a factor and x + 1 is a factor. And then using synthetic division, you make sure you put, because you have x cubed here, you're going to have a 1 for the x cubed, and then there's no x squared term, so you're going to put a 0 in, and then there's a -13 and a -12. And then when you do the synthetic division, you end up with a quadratic of x squared minus x minus 12, and that factors into x minus 4, x plus 3. So your final factoring is x times x plus 1 from the -1, 0 that you had used in the synthetic division, and then x minus 4 and x plus 3. So reach out anytime any of you would like to have a Zoom meeting for help, or send me questions that you would like me to put on a little video. I'm happy to help out.